Right. Welcome, everybody. We're going to talk about streaming with Heron on the Kubernetes and Docker stack today. I'm Ron Wilcom, Chief Engineer at Next Century Corporation. We had a discussion of this Heron. Probably it might have been a year ago. I'm not sure how long. That was on a different stack. Some of this is similar in that earlier discussion we had, but I'm going to get into a lot more details on actually building a topology. And of course, there's some differences here when we're talking about this stuff running on Kubernetes as well. There will be some reiteration, I guess, on just general cloud analytics, the streaming, some advantages of Heron, and the concepts of Heron versus other systems. And again, we're going to talk about hopefully get into the details of putting together a topology in Heron using Java, and even show off some of the failover capabilities that Kubernetes and even Heron internally provides, which is one of the big draws for me in this system. So cloud analytics is really three types: batch, which basically is sort of the slower version of the cloud analytics at this point, where you're basically pushing around large batches of data, creating map-reduce jobs, et cetera. Micro batch, where you are, it's a similar thing, but you're actually creating smaller batches of the same types of data and pushing them almost along a type of stream, where each point of the stream is going to process the batch. And then the streaming type, which is what we're going to talk about today, where we're going to try to process real-time data. We're going to analyze and act on it in real time and even provide sort of continuous query results. It's something that you can do window transactions on, but you want to make sure that you're not holding up the stream too much in those cases. So we'll talk a little bit about that too. Three V's of big data: volume, velocity, and variety. So the key here is that we're trying to look at the velocity factor here to try to get the data across to the customer or the user in real time. Obviously, volume is always a factor, how much data you're going to push through, and then the variety of the different types of data you may be pushing through. But if you're trying to get data through fast, you probably should consider streaming. So what is this good for? I mean, obviously you can realize this pretty quickly, but some will say it's good for anything. But you could probably use this as at least a complementary to batch processing as well. But here's a list of things that are pretty obvious. Point of sale, detection of system problems is an interesting one. Live geolocation movement, radar and signals events, all of these types of things that you're going to want to know when something's happening in real time if you're tracking, people or things. So streaming analytics and processing in general, we're looking at trying to get the real-time events in seconds to minutes. The one thing I talk about there in that first bullet about the live sensors alerting and collection is a stream. When you think about programming at a low level, you think about streams differently, where you're looking at like streaming bytes and trying to get bytes recollected and reformed. It's not really that way here. I mean, you're really streaming across tuples, which are, kind of a property bag, or you can stream across an object. And in each point along the way, you're generally going to look at that object or look at that tuple and do something with it. We are basically building a directed acyclic graph here, so a DAG. So in order to process this data, you're going to have to think a little differently than I think in a traditional process. You have to really think at a micro level and break down your processes really small and let your data kind of ping across those points of processing. We'll get into that a little bit more. Some examples of streaming analytics is Apache Storm, IBM Infosphere, which is also known as Distillery, Twitter Heron, which is what we're talking about today, Tibco Streambase. You could probably keep going on and on. Some of those are commercial, some of those are open source there. So what led me to research Heron and all the stacks that it operates on? So one of the things we do with the customer is process a ton of data. We have a ton of processes that work across that data. And one thing that we have come to realize is that manually managing all those processes across a lot of different servers is pretty monotonous and time consuming, and a 24-hour-a-day job. So what we wanted to do was find a solution that would not only obviously be more efficient in terms of streaming the data across, but would also be self-healing and self-monitoring. And that's one of the reasons why I landed on Heron, because when it's riding, Heron itself is self-monitoring, but when it's riding on top of some of these frameworks, it's self-monitoring out to the next level as well. And we'll talk about that. It also makes it easier to deploy it. So when you're pushing that out across 100 servers, you don't have to say, well, I'm going to push this one process to server 53. You're basically creating your streaming processes in one spot, and then they spray out across the resources. We'll get into that quite a bit. So Heron itself was originally developed by Twitter. The main guys that led this were Karthik I can never say his name, Ramasamy, and Sanjeev Kulkarni. Okay. What's interesting about Karthik specifically is that if you go on to the Slack page for Heron, he's there every single day. I have conversations with him on a daily basis almost. You can ask him questions. He's got a team of people that are working on this project, and they are really active in helping you out and getting Heron to the next level. It was actually a rewrite of Apache Storm, which was also led by Karthik, and it's actually backwards compatible with Storm. So if you have a Storm topology, you should be able to port that very quickly to Heron. This project's actually been around since 2014, and Twitter was obviously the first adopter of it because they wrote it. And then they made it free and open source software in around 2016. And now, obviously Twitter, Google, Microsoft, there's a lot of different groups involved in this project and using Heron today. It does have multi-language support. Most of them are Java-based, but Java sort of was the core first one. They're supporting Scala now, Python, Groovy. I haven't seen Groovy, to be honest with you, anybody talking about Groovy, but I know that Java, Scala, and Python are definitely used right now. The company, as they pulled it away from Twitter, a group called Streamlio, which is led by Karthik again, has basically took it under their wing, and then they just donated the entire project to Apache last month, in February. But as of this month, they're now working on their version 18, and they're porting all of the packages and everything to be org Apache Heron. So that's in process right now. 18 is not out yet, but they're on the cusp of releasing that.
Is that an incubator, or is that a full release now?
It's been incubated for many months, and now this is the full out version. Yeah. So other things about Heron. So isolated processing. There's a really clean mapping from your logical topology to the physical deployment of your nodes. We're going to talk about a lot of these things, but I'll just run through them quickly. So you can specify the resource allocations, and you can configure that per topology. And within the topology, you can configure how much resources are being used by each node. I'm going to close. Shares hardware resources with any other system. So basically what it's saying there is you can spray this out across a lot of different parts of your infrastructure, and that should reduce your cost. There is no single point of failure. So again, there's automatic failure restarts and reallocation. Back pressure is a kind of a unique thing to Heron. So as data is pushing through the topology, if one of the nodes starts to not be able to process fast enough, it will push that message all the way back to the source and actually slow down the data processing temporarily until the system fixes itself. Elastic scaling is something that I've been waiting on for at least 6 months. It's part of their system, but of course, the stack I was doing before, Mesos and Aurora, supports elastic scaling. And then I moved to Kubernetes, and Kubernetes isn't properly supporting elastic scaling. So I'm still waiting for them to fix this in Kubernetes. Higher throughput at scale, so it's been benchmarked that it's at least 10 times better than Storm. We also have folks on the inside that have migrated from Distillery, and they also say it's much faster than Distillery or IBM Infosphere. Modular agnostic to resource managers and schedulers. I say somewhat. The idea there is that you should be able to deploy Heron across different types of stacks, whereas things like Storm were kind of fixed in their own way. this is more modular. I say somewhat because it takes a lot of work, trust me, to get these stacks set up and to get these things running on them. So it's not just like a walk in the park to get it going. And then Streamlets is a new thing. I haven't really messed with it much, but it's actually an API that makes it very simple. It makes it a very easy and simple way to create, to build a stream processing topology. I personally don't use it because I like to get into the guts and build the topology from scratch, but apparently it's pretty popular amongst certain people. Anyway. So some of the concepts of Heron. So I keep saying topology. So what's a topology? That is your directed acyclic graph. So when you start to think about the way your data flows through the graph, it's the logical way that it flows through there. So this is basically representing that DAG. We will have a spout at the beginning of our topology. That's going to produce the data or push the data into your bolts, which are the processing points. The things that are important about a spout is that it will actually do the back pressure management for you. So if the data is flowing all the way up to like bolt 3 and bolt 3 starts to create back pressure, the data will actually stop and push back all the way to this point. So it actually holds back at the spout level. It's actually a replay point as well. So if you're working on trying to use ACKs and NACs, things like that, the replay point rolls all the way back to your spout. Generally, you're going to find the spout to be something like Kafka or NiFi. It could be HDFS. You could be reading from files and pushing things in. That's not really a stream, but and JMS, things like that. Again, bolts are your workers, so that's where you're going to transform, filter, join data. The data stays live. You could write it out to push it out to a system at any bolt, but what you want to do is keep pushing that data along the stream. Get out of the way. I can't read it. So there's multiple types of stream groupings, and as you define your topology in Heron, you can define how the data goes across your stream. So if you have like 5 instances of this bolt, you can tell the previous bolt or the spout coming in to shuffle group your data. That's pretty much the norm. So what you want to do is load balance your tuples running across from that spout into all of those bolts. But there are also different other types of streams you can add. If you do like a field streaming group, it will take you can look at a value within your tuple and it will actually direct it to certain bolts based on the value of your tuple. You could do direct, which is one way. You could say all, which would replicate your stream across all the bolts. Or you could do global, which I don't even know what that is, join and narrow to one. So if you have a ton of data flowing into one bolt, I guess you could push it all into a single. I don't know why you'd ever do that, so I'm not even going to talk about it. So now you have a topology defined. You want to distribute that across your cluster. Maybe there's 500 instances across your cloud. So how are you going to deploy all of them? How are you going to manage all of those resources? How are you going to monitor the performance? I mean, here you've got maybe one node over here that's failing. How are you going to keep track of that? And then how are you going to deal with one of them failing? So let's say one node out here fails. Are you going to sit there and monitor that all day? You probably are not going to want to do that. So you don't want to think about things that way anymore. You want to think about them this way, which is pets versus cattle concept. I know I always rail on this. So people that have come to my meetings are probably like, God, I have to hear this again. But the idea here is that, and it really boils back to what I've been living for the past 7-8 years, where we push out processes. Those processes are closely monitored. We will reset them manually when they have a problem. So you kind of think of those as pets. You know exactly which server they're on. It's kind of a long day and a long night when that happens. If you think of cattle, you think of the process as being sprayed out anywhere. If the process dies, it will be recreated or replaced. So you're not monitoring them all day. You basically let the herd go, if you will. So the stack we're going to talk about today is this one for Heron. This is sort of, I'd call this the new prescribed stack for Heron. The old prescribed stack was Mesos and Aurora. Aurora was a Twitter scheduler, but they've broken away from that and have really adopted the idea of using this stack, which is based in Docker, which is your container platform. Kubernetes is the next layer, where you're going to use Kubernetes to orchestrate the deployment of your topology and all of the pieces of it. These parts in between are just really just requirements where you'll have, you could replace Gluster with other types of distributed file systems, but it has to support persistent volumes, and we'll talk a little bit more about that. But I'm using Gluster on my stack. Zookeeper is really basically a configuration point, and Bookkeeper is a way to distribute storage across the services as well. So those last three things are really just byproducts of things you have to have in the stack in order to support Heron in general, and then you put Heron on top of all those things. I can tell you that it's not simple to get all these things put together. I have a ton of notes on these, and so if you ever try to do it, definitely talk to me, and I'll help you out. So again, we talked about it being modular. So as a sidebar, here's some other stacks you could use. The prescribed stack back in early 2017 was the Mesos Aurora stack. I was using HDFS to get the deployment across. You could use HDFS, Yarn and Heron. You could use SCP and Slurm and Heron. There's a lot of different combinations. But generally, right now, they're looking at this Kubernetes. And I think, at least comparing my experience, comparing Mesos Aurora to Kubernetes is just crushing it. It's much, much better. So let's get into some details about how this works. So basically, this is sort of logically how the VMs or how your cluster would lay out. You have a Kubernetes master, and some of these you would certainly replicate in a production environment, but the Kubernetes master is built up using kubeadm, which is basically the app you use to install Kubernetes. Then the parts that end up on your master are the kubelet and the kubectl, which kubectl becomes your client to talk to kubelet once it's running. The kubelet is really the container manager itself. So once that's running, that's managing and orchestrating Docker at that point. You have to have Docker installed. And once you get the Kubernetes master installed, you'll find that it actually installs a list of different things into Docker that is actually part of its running stack. Obviously, API, controllers, schedulers, all those parts are in there. Whereas before, where I was using Mesos and Aurora, where Mesos was basically the resource manager and Aurora was the scheduler, those things are all combined now inside of Kubernetes. So you get it all in one package. WeaveNet is something I'm using, but you could use any container-based network here, like Flannel's another example. And then the Kubernetes Dashboard is sort of not something they seem to highly support, but I think it's been very helpful. So I'll show you what that looks like as well. And then you'll have a number of nodes. So all of your nodes will be lined up out here. And the nodes will basically be the kubelet running out there alongside Docker. So they become basically nodes that are controlled by the master. And all of your images that end up getting deployed through Kubernetes end up out here as a Docker image. I wish that would quit popping up. It's driving me nuts. It's coming up every time I move my mouse.
When it pops up again, though, on the there.
It's still going to do it to me.
Oh, is it?
Yeah. I'm doing that because I want to go across these tabs. But all right. So and then GlusterFS is along the bottom there. The one thing I have noted there, these little PVs, those are persistent volumes. Those are things you have to set up on your boxes or on your VMs, and they will come into play later as we use Gluster. We'll talk about that some more. So, so now what you have is your environment set up to actually deploy some things. Basically, what happens here is you're going to set up persistent volumes. You can set them up at all of them on your master. You can set them up across different nodes. But what's going to happen is that's going to get exposed through Kubernetes so that it can basically write data to your disk using the Gluster file store. Heketi, just a sidebar. Heketi is a way that, so setting up persistent volumes is kind of a manual thing, but Heketi, which I'm not using on the outside here in my examples, but we are using it on the inside, is another thing you can actually lay down in that stack, and it will create the persistent volumes for you on the fly. So once you install Heron, this is sort of the picture you end up with. It ends up installing the Heron Heron admin tool on Docker. You need to install Bookkeeper on Docker, Heron API, Heron Tracker, and Zookeeper. You will also need to install the Heron client anywhere. Basically, I actually have it installed on the same box that I'm running master, but you can install the Heron client anywhere, and this is where you'll push deployments from. The thing to note here again is that Bookkeeper and Zookeeper are going to want to hook up to those persistent volumes so that it can persist files out to your disk. You'll also want at least 3 Bookkeeper instances and 3 Zookeeper instances in order for those to, if one goes down, it doesn't like wreck all of your data that it's using for configurations and for deployment. Yep.
Do you have Zookeeper and Bookkeeper together installed, or do you have them separated on 3 and 3?
They would be, so you deploy them to Kubernetes, they could end up anywhere. Okay. Yeah. But you'd want to do 3 instances of it when they're pushed. I have, in my example, I have 3 Bookkeeper persistent volumes, and I got lazy with Zookeeper, and I installed that one with no persistent volumes, and when things bounce, it gets bad. So then I have to clean things up. So you really want to have that in a production environment replicated. So once you have all that installed, if you went out to your command line and used Cubectl, which is sort of your main command line way to see what's happening inside of Kubernetes, if you do Cubectl get pods, pods are basically containers that are running in Docker that are being controlled by Kubernetes. So in this case, you'll see a list of your bookies, which are your Bookkeeper instances. There's a couple auto recovery instances that gets created. You'll see the Heron API server running out there, and the Heron tracker, which is really the API for the Heron UI. And that's something that in older systems, it was really critical, but here it seems to tie it all together as a bundle. And then there's ZK0, which is my one Zookeeper instance. I should see 3 of those out there. And that's, you can see how lonely it looks, and that's why things go bad when it gets bounced. You could also do all namespaces. So one thing to note about this is that Kubernetes is going to create different namespaces out there, and it's going to install its own stuff to its own namespace, and then the default namespace is where everything else goes. So if I was to do all namespaces, I would actually see like a lot of extra Docker images running that are all based around Kubernetes. Its processes running. A couple other notes down here, you'll see Cubectl logs. You can add the pod name and the deployment name. That will actually dump out any logs associated to that specific image for you. Good for troubleshooting. And then the Cubectl exec with the pod name, with the deployment name, will get you to a bash command line. And then once you do that, you'll be inside the container of the thing that's running there. So if I did Cubectl exec IT, I'll just say bookie-0, and they don't all have deployment names. So when you get into some of these other ones, they do. But what would happen is it drops you into another prompt, and then you'll see exactly what's happening inside that container, logs and everything else. It's obvious. It's pretty critical when you're trying to debug stuff to get to that level. Yeah. So then in order to get things deployed here through Heron client, you'll have to run a proxy. So Cubectl proxy, you can pick any port. And what that's doing is sort of getting you into the ability to interact with the Cubectl and the kubelet that's running on the master, and then the APIs that are happening there. So to submit your topology, that's basically this line here. Heron submit Kubernetes, and then you're going to define the service URL. So you can see how long this URL is. It used to be that you would just deploy it to Heron API server, but now basically the API server is running inside of Kubernetes. So this is basically pushing across Kubernetes services, finding the Heron API server in there. It's running on port 9000, and it's going to submit this jar file into this API server. As it pushes across, you have to tell it like what your class name is for your topology, and then here you're naming the topology. This name has to be something very simple, and for some reason, I don't even think it can have like camel case or anything. It's got to be like all lowercase. I don't know why, but it'll break if you don't name it right. It could be any name, but specific
but by simple,
signature.
Lowercase.
Yeah, yeah.
Lowercase, all letters.
So once you submit your jar file, these are kind of this is sort of the way things happen. Your jar is pushed across through the Heron API, which again, it's running inside of Kubernetes on a Docker as a Docker instance. It's going to push the jar file across into Bookkeeper and store it on underneath the Bookkeeper to disk. And then it's going to apply a packing algorithm to it. It's going to read your topology and apply what it thinks is the best fit across your spouts and bolts in terms of creating Docker images, containers, et cetera. We'll talk a little bit. We'll definitely talk in more detail about that. But your spouts and bolts are going to break up, and depending on how many instances you told it, how much memory you told each spout that it should have, how much CPU it needs, et cetera, the packing algorithm is going to take a best guess at that. Kubernetes knows at this point how much across all of these nodes, how much CPU it has, how much RAM it has, how much disk it has as a whole, and it's going to deploy your topology across these nodes based on what the container is going to ask for. So the container might hold 3 or 4 bolts in it. Actually, maybe this next, yeah. So as the packing algorithm executes, it's, in this case, this is an example. It's going to create 4 containers. It's going to put some spouts and some bolts in each container. It does try to spread them out, obviously, because that creates the failover. And it's going to create what's called a stream manager in every single one. And that's how the data is going to stream between the containers. Again, this is going to be, the packing algorithm is going to be a best fit, but it doesn't know what your resources are yet. So it might build these up and then deploy it. And then it might tell you that you don't have enough resources to deploy it across your cluster. So and then you might have to tune it differently and do it again. Or you might have to get more resources if you have to have that much space for memory or CPU.
Question. So conceptually, you have multiple nodes each running a spout, and all the spouts, they read from the same source. Do they coordinate to make sure the data is not duplicated?
You'd have to do that yourself. So if you're reading from if they're all reading from a single Kafka queue, for example, then it should handle that, right? If you could have multiple spouts reading from multiple, different resources, or different types of sources. So like the example we have inside, we have multiple sources coming into our topology. So we're reading across all of them, normalizing it and pushing it into the rest of our topology for processing. So it really is up to you to manage that part in terms of how the data gets pulled in and pushed across your topology.
If you're reading from a file, for example, on HDFS, then you have to.
You'd have to do something about that one yourself. You'd have to make sure one spout is only reading one file, right? For example, generally my suggestion would be to prop something up. If you had files, read the files in, push them into something like JMS or something that would manage that across the spouts. Spouts reading files directly, probably not the best. That's my opinion. I mean, I don't know. Somebody might fight me on that. But the other thing here is, even though this one's showing, actually this one's not. This one's showing like 3 containers have spouts, and this bottom right one does not. So a spout might not end up in every container. It just depends on how many instances you're asking for. In terms of bolts and spouts. So once the package has been figured out for these containers, it's going to push them to Kubernetes. And so now we've got 4 containers that are going to try to be pushed across the nodes that Kubernetes knows about. So now we have, and one side note, I don't think I said it here, but it actually creates one additional container, and that container is used for topology management. So there will be an additional container that is built outside of the ones that are built for your specific topology. So now we've seen that the topology has been deployed across these nodes, and there's multiple containers. Each one will have bolts and spouts, et cetera, et cetera. And you really don't have control over which ones these go to, and you shouldn't care. So once that's deployed, your topology is going to spin up and it's going to run. So once you get things up and running, you may want to take a look at, how things are deployed. I found a really easy way is to use this Kubernetes dashboard. So what it looks like is this. This is running, so just a sidebar, I have 7 VMs running on our OpenStack system. These are, they're varying sizes in terms of disk space, RAM, things like that. So you can mix and match how much each VM has, and Kubernetes is going to manage how much is reported back to it, and it will push data out appropriately to that. So these will basically match up to the specific nodes that I have available to me in Kubernetes, as you see here. If you click on any one of these, it'll drive you down into that specific node. And then you're going to see things like CPU allocation, memory, pod allocation. And this is based on how many containers or whatever got pushed. Some of them are containers about my topology. Some of them are straight up like Heron API might be sitting right next to my own container, right? So if we scroll down, again, there's tons of stats in here. If we scroll down, we can see that this one has one of my containers, which is called tcop test. It's holding Bookie. It's holding the Heron tracker. It's holding Zookeeper. It's holding another Bookie in there. And the Cubectl, the Cube proxy and Weave are on every single node. That's how it's talking back to the master. But you'll find that any given node in your system might have one to many things happening and could be completely unrelated. Like if we go to just tcop test 5, much lighter allocations going on. And if we scroll down, we'll see that the only thing it has running on it is one of my containers for my topology, along with the WeaveNet and Cube proxy. So this is just a good way to kind of get a view of how your data, how your containers went out across the network. Once we, yep, go ahead.
In that page you just had on, I saw restarts on there. Is that restarts from failing, or is that restarts that you did manually, or?
It's let me think about that. I know it's definitely from failures. Sometimes we'll get failures. I don't know if that's counting up the restart since I deployed it or not. Probably if you were to do a full undeploy, then it's going to start to count over. So, but most of the time you're sitting things like WeaveNet, for example. Like I haven't reinstalled that for, I don't know why it says 2 days there, but that's probably since it's been restarted. But that and Cube proxy, those haven't been reinstalled for months. So actually it might tell me on this other view. 1 second here. Oh, here's a kind of a better idea of that. So here's Cubectl get pods. I don't know if you can see that far. You probably can't. Let's see if I can't blow it up. So for example, Zookeeper, it's been restarted 18 times and it's 62 days old. So I guess I deployed that 62 days ago. And then you look back at like Cube proxy on this system, that's been 119 days. So these things have been sitting there for a while. Here's one that this Cube scheduler has been restarted like 1,500 times. So some things have issues and it'll bounce them and restart them on its own. It's actually one of the nice things about it is that stuff's happening and you don't even know it. You know what I mean? Like it's fixing itself all the time. Basically what's happening here is this is going to get into some of the details of what's happening within your topology. With Heron, like I said before, that's going to create a Topology Master, and that's going to sort of monitor each container that's out there and make sure that a specific instance is not having a problem inside of a container. So when you think about the container as a whole, that's going to be managed by Kubernetes. But when you look at the instances inside of a container, those are managed by Heron. So each instance inside of a container, one single instance could have a problem. Let's say memory blew up on one of your bolts. Heron will recognize that and it will restart that single bolt in place. If a whole node goes down, like one of my VMs gets shut down, that's going to be handled by Kubernetes. So if I have one of my containers on that VM, then it's going to recognize that the entire container went away and that we need that restart that on a different VM, and it will do that for me as well. We can demonstrate that at the end. I can kill off a box and we can watch it recreate some stuff. But that's what this picture is talking about here, where the Topology Master is managing that. We kind of already alluded to the fact that each container has a stream manager. It also has a metrics manager, so you can take advantage of just adding metrics about your bolts and spouts inside of sort of a self-contained thing there, and it will report back through the Heron API. And I'll show you the Heron API and the Heron UI. Instances are spouts and bolts. We just went over most of this, so we're good. This is basically the picture we were just looking at before. So this is the Heron. Heron provides this Heron UI. What's interesting about this is it's a pretty good tool just for generally seeing what's going on with your topology and how much data is flowing through it. But the Heron Tracker API, which is also part of this, is a full API. You could write your own user interface to monitor your system if you wanted to. And you might be able to write a better one than this, I'm not sure. If we want to take a quick look at that. This is a topology that I wrote, and we're going to get into some details on this in a second. But what we're looking at here is an air traffic data source. This is pulling from OpenSky, and it's pulling air traffic data every 10 seconds. Whatever it has, it pulls it in, it creates tuples out of it, and pushes it through the stream. So here I've got what's considered to be a normalizer node. So I'm pulling in that raw data, and now I'm normalizing it into values that I want to look at. I've created this thing called a punching bag node. And what I use this for is to sort of test how Heron reacts to things. So I have this hooked up to Redis, and it responds to Redis commands through like PubSub. And I can say like, hey, take the memory up on this specific instance and just, blow up memory at this point and see what Heron does. So we can actually play with that as well. So router node, and here I was sort of learning like, okay, how do I split streams? How do I bring them together? Activity enrichment, activity alerting, location enrichment, location alerting. And then I wanted to bring the streams back together and create a publishing bolt. So that's basically this layout, and we'll talk about that a little more. But what's cool about this is this thing's monitoring memory that's happening across your entire topology. It's looking at the GC situation. Back pressure is monitored here. Everything's 0. But what happens is if I start to mess with the punching bag bolt and crank up memory, then you'll see like back pressure will spike up, max capacity will spike up. We'll get some different issues going on here. And this will start to tell us that that's going on. You can also say like, okay, location alert node, where are you? So here's the 2 instances. I have 2 instances of this specific type of bolt, and they're across these 2 containers. The container as a whole has 4 other bolts in it, as you can see as I click on them. And this is basically part of that packing algorithm. Like I didn't get to pick how this laid out. Heron did that for me. For any particular node, this type of node here, I could scroll down, and now you can see that how much data has flown through this since Tuesday night when I started it. So you'll see all-time counts of how many tuples it emitted, how many it executed. And I have actually acknowledgement running on these as an experiment, so it's actually sending acknowledgements back down to the previous bolts. And then you can actually break down into singles here, looking at the emit counts of each specific instance of your bolts. So we'll get a little bit more into this. We'll look at this a little more as we maybe hit the punching bag bolt or something. I just walked you through all that. So developing these topologies, how do you do it? So again, we've talked about tuples, and that's the type of structure you're going to be sending across from one node to the next. I've written, again, this Heron test topology that we're going to use as an example. And we're going to talk about how to write the spouts and bolts. We're going to look at configuring the topology itself. We can look at the guaranteed delivery, which is to send acknowledgements back to previous bolts and tell them that you've already processed the tuple. But again, the spout is the relay point. So I don't feel like I ever fully got through all the way to really do acknowledgement and guaranteed delivery yet. So I'm not satisfied with that, the way it sits. And then exactly once semantics is another one where you can force and make sure that the data or tuple is only processed once, something new that I haven't been able to get into yet. So we just went over this live, I guess, but just to reiterate, pulling in open sky traffic, the spout reads that in, sends it to the normalizer. This guy's going to turn it into the tuple that we want. This is the punching bag bolt. It's hooked up to Redis for PubSub. These are all bolts we talked about. The activity enriched bolt pushes data out to Redis as well in PubSub, and the location enriched bolt pushes data out to Redis as well. And then at the very end, we have 2 bolts here. They're looking for like, is the plane on the ground or is the plane in the sky type of alerts, really simple. And it's formulating a new tuple and sending that down to the alert publisher bolt. And then that's pushing out to Redis as well. So the things I was trying to do here is, just get a live data feed going, try to understand how would you break this out into these microservices, enrichment and alerting, I wanted to try guaranteed delivery. Again, I'm not satisfied with that at the moment. And then test adverse conditions, and that's why I have the punching bag bolt there. And then splitting and joining streams, publishing the alerts out to Redis, and then the deployment environment in general was something I wanted to get familiar with this test topology. Two big things that I really have been looking forward to working on is the elastic scaling piece. Elastic scaling, again, it's fully supported in Aurora, and of course I moved to Kubernetes, and now it's not supported in Kubernetes yet. But what's really cool about that is the idea that the bolts, when we talk about back pressure, where the bolt is over processing and can't keep up, and it starts to let the data slow down, the idea with elastic scaling is that once that back pressure is recognized, is that the Heron system is able to recognize that based on algorithms, and it will actually grow the number of instances of that bolt automatically within your stream, where it should then take the back pressure off and be able to process more data. The thing I've learned recently is that they haven't figured out how to back off the number of instances yet, so it will grow and take up resources, but I don't think it'll shrink yet. So those are some things I'm really looking forward to. It was one of the things that drew me to Heron, that, you know, thinking that it could do this, but they're still just in the works. So just real quick, can you guys see that code up there, hopefully? So developing a topology, the first thing you want to look at is the tuple itself. So to create a tuple, there's obviously helper classes in Heron. These packages names are all going to change, by the way. But there's fields and values. So you're creating a tuple schema first, and I'm going to create my fields, and these are the name of my fields. And then you're basically adding values to those fields. So that's going to build up your tuple. The tuple is what you're passing from node to node along the way. If you don't want to do tuples, you could also create objects, and as long as it's serializable in Java, you can push that over so across the topology as well. So basically, if I create an object called airplane object, I can, as long as I've created airplane as bytes, I can shove that into the values as well and have a one-to-one. The disadvantages with this, I don't think there's a lot of disadvantages in terms of speed unless you fatten up your object too much. But where the disadvantage comes in is if you want to use the different types of streams where you say like field-based, you're going to have to pull out the value and put it in your tuple in order for the field-based streaming to work. But if you're not doing things like that, objects might be okay. We're trying to stick with tuples in our current implementation and keep that as our basis, but we're not sure how long it's going to hold up. We'll see.
Tuples are not supposed to contain objects. Tuples only contain primitive values.
Yeah.
So you have to disassemble the object.
Yep. Yep.
And what do you have nested? How does that work?
Well, the only thing we've had to deal with so far, like we put arrays inside of the values, but we haven't done anything more than that right now. So we're trying to avoid the complexity basically on the tuple, and make it as simple as possible as the data flows by. So. So then the writing the spout. Basically here, you're deriving, in this case, I'm deriving from base rich spout, which is one of their classes, but there's interfaces below this, and you could write it even more raw if you wanted to. Here I'm defining the open call, which is going to be made when the spout is created. So that might be where you want to prep up your data source, open up this, JMS connection, whatever. You're going to get a close call when the spout shuts down. This is sort of the key call here. Next tuple. I wish I could point to it without that thing coming up. Next tuple is what's going to get called every single time that it wants to pull data out of your spout. So what you want to do there is do an emit on your collection, on a collector, which is defined up top here, and it's passed in. The spout output collector is going to allow you to omit your data. So here you're going to create a tuple, and you're going to add your tuple to this specific emit call. If you want to do acts and fails, you can add a message ID to this, and that will carry along as well. Oh, get out of the way. I think that exits the whole presentation. Yeah. There it is again. So the declare output fields you have to do in every bolt and spout. You're basically telling that bolt and spout what fields to expect as they come in from in the emitter or pushing out from the emitter. Defining a bolt, again, I'm going off a base rich bolt. You're going to get that output collector sent to you on the prepare call automatically. Again, you'll need to declare the output fields that are happening inside here. So the main call here is execute. So you'll get an execute call. It'll pass you a tuple. And inside of that, you may do all kinds of processing of that tuple. You may write out to Redis. You might write to a database, whatever you want to do. But at the end of the execute, if you want the data to carry forward to the next bolt, you'll have to do a collector emit, and you'll pass that tuple along. If you do a collector ACK, then you're acknowledging to the previous bolt that you have finished processing that tuple. So that after you've created a bunch of bolts and spouts, you have to stick them together. So there's a thing called a Topology Builder, and the Topology Builder is where you're going to create that acyclic graph. This is a pretty high level here, but we create the builder. We're going to name each node along the way. So there's air traffic data source, and I'm going to create the air traffic spout there, and I'm going to define how many instances should be included in that. And then I'm going to define some bolts, normalizer bolt, how many instances there are, and then I'm going to do a shuffle grouping off of that air traffic data source. So basically what this is saying is create a single spout, and I want a basically round robin or load balanced feed to 4 instances of the normalizer node, right? And then it keeps carrying on. So from the normalizer node, you'll also do a load balance feed to a router node. And I'm only going to have 2 instances of that. So you kind of have to, the thing about instances, you'll have to figure out tuning wise, like how many instances do I need to process this data? The example here is like normalizer bolt might be a little heavier to do processing. So I'm going to have 4 of them where router's doing nothing but splitting the stream. So I don't need as many.
This is where the Streamlit API replaces this, right?
It does, yeah. So Streamlit API, you sort of are like, you know, pushing in your instructions directly into it, and you don't have to kind of know the lower level stuff.
But you don't have fine-grained control per se.
Right, you actually don't control it at all. Like you don't get to control a lot of the way that the graph's set up. So here's an example of splitting it across 2 streams. The router node itself is telling the router node to shuffle group across the location stream, which is now a named stream. And that named stream would be part of the definition in that location enrich bolt. Again, with the alert stream as well, you'll define the alert stream inside of the alert enrich bolt, and that's where the router node is going to be able to push data across. Once you're in router node, then router node can define which direction data flows, and it will specify which stream that data is flowing to. Let's see here at the end. This is joining 2 streams together, I think. Let's see here. Yeah, so the publisher node, I'm going to have 4 instances of that, and it's going to create shuffle grouping of pulling data from the location and activity stream. The next thing that you have to know is actually defining what resources your bolts and spouts take up and your containers as a whole. This is changing. I wouldn't say significantly changing. The concept's the same, but Heron is now adding a whole boatload more of these types of settings to let you more fine-grained control this. The last release they put a new packing algorithm in it, and it exploded, and just like I went from like 5 instances to like 18 instances or containers, and it couldn't even deploy on my setup. So I complained about that, and they're kind of rolling that back and fixing up the way the packing algorithm works alongside with being able to specify at fine-grained levels, like how much CPU each bolt and spout can take, things like that. So this is an example of that. It used to be that stream managers, how many of those you defined would really turn out to be how many containers in the original packing algorithm. But that doesn't seem to be the case anymore. It kind of blows right past that. And so that is now, again, these are being changed. So I think you'll probably find something like set min number of containers will probably be the type of methods that they'll have here for setting the configuration up. But here you're defining, with this air traffic data source, I want 500 megabytes. I want this to have 500 megabytes of RAM, for example. Here in the older system here, you couldn't do much more than set RAM per bolt, but they're going to expand that and let you set disk and CPU requests as well. This, in the older version of the code, you had to set whole container disk and CPU. And then finally, you're submitting the topology to the submitter. So this is sort of the code that runs when you actually deploy your topology. So we can look at, this is the punching bag bolt. I'll play with this live so we don't have to go over it. This just to note, the elastic scaling is called Dalian. It was actually written, I think, by Microsoft developers, since there's a lot of different groups in the mix working on this project. And this is the stuff that's self-healing. You can have configured thresholds and prevent back pressure scenario that we already talked about. You can do what's called apparently, having been able to test this, you can do an invasive health monitoring with Dalian, or you can do non-invasive where it just alerts you. Invasive will actually dynamically alter your topology on the fly, where non-invasive is just going to alert you about it. There's a good white paper on it at that link. And so if you read that, it gives you all the basis of their algorithm for doing this.
When you say alter the topology, you just mean the number of
Yeah. So like if one
topology itself, it's just
you're right, not the DAG,
okay.
but the actual instances of a particular bolt, for example, might expand by 1 or 2,
Okay.
and it'll redeploy it. Yep. So the code examples, I have my code examples are out there, and on a GitHub if you want to get to it. So if you want to look at all the code that made up the topology I talked about, it's there. And then they have their own examples as well up on their site. And that's probably not the right link anymore. But let's just jump out here and play for a second. So here we have our running topology. If I jump out to, no, you are not being friendly to me right now. All right, so I'm going to shrink that up a second. So this is actually a Redis client right now, and what we're seeing is the data flowing through the running topology that we have here on Heron that's monitored here. So as data is flowing through, we're looking at all the stats we talked about before. This is the logical representation of this, and this is basically the physical representation because it's showing you the containers, the instances, and how many, and the containers and how many instances are running and which ones are running in each container. So here we have data, it's flowing out. This is live air traffic data, and it's flowing through from left to right. If I was to stop this guy, let me run that client again. So I have, you can't read that, but what it says is publish, punching bag, 15, clear memory. We don't want to clear it. We're going to mess it up. Leak memory start, 1000. So that's going to start, it's going to start messing up the punching bag bolt, and it's going to start adding to its memory 1000 bytes at a time until the thing explodes. So if I hit enter here, it just sent that out. And so what we'll see in a few seconds is this punching bag bolt. There's 2 of them. That's 14, instance 14, and that's instance 15. So the punching bag bolt lets you target very specific instances that are out there on your topology. It doesn't refresh itself, so I'll have to kind of click back and forth. That's one thing. That's one thing you could improve by rewriting this thing. And we'll wait a second. It'll take a second for it to kind of degrade, but we'll start to see spikes over here where it starts to get into some pain points. There we go. So if you look to the right here, we've got a spike. The GCs per minute are freaking out. What you'll also see, you'll start to see max capacity freaking out and CPUs freaking out. So on this specific instance, it's starting to hurt. And so Heron is monitoring this right now, and it will, if the that specific instance starts to get too bad or starts to degrade to the point of unusefulness, it will kill this bolt and recreate it, just that instance. And we could probably crank it up and make it worse. Let's see. Some other things I could do with that punching bag bolt is I could tell it to send only failed acts or send a percentage of failed acts versus real acknowledgements. So when you see that, you start to see other types of things happening in this view where if you scroll, it's not going to be doing it, but you'll see failed count will go up, things like that will happen as it's monitoring the situation. So it's really getting in the red here.
Will Heron do anything with the fail counts? Like you said, a threshold where it says fail counts is higher.
You can't. So I thought that's how I interpreted how it would work at first. But what the acts are really for is for the application level development, not for the system level development. So what you're really doing there is you're creating acts and fails for your own sake. And you have to manage those on your own. One thing that happens is, again, it will actually, if you fail it, it will fail all the way back to the spout. So you'll have to have something at the spout level that's able to track the IDs that you sent forward. And when the act comes back that it's been taken care of, you would clear that from your spout as not needing to be replayed.
Yeah.
But if you get a failure, you're going to have to handle the replay yourself. Apparently, there's some things built into Kafka that can do that for you. I haven't dealt with that. But there are basically those types of sources that can do it for you.
Okay.
So let's see where we are here. I don't know if I'm going to kill it enough while we're sitting here. But basically, you would see this thing actually die off, and the instance would actually disappear for a moment, and it would come back to life. The other thing we could do is actually kill a whole VM. So if we kill a whole VM, Kubernetes is going to take over, and it's going to redeploy everything that was in that VM. So if we look at this TCOP test 1005 instance, it's running one of these instances here from, I don't know which one it is, but we'll find out when we kill it. So if I go to my list of VMs here, just reload this.
So much cleaner than the one off the flies, isn't it?
Yeah, it's fun. All right. So if I go to TCOP test 5 and I do a shutdown on it. What's that?
Ouch.
Let's see what happens. Sometimes I have to do it twice in here and I have no idea why.
Like real world.
It is. I mean, that's why, I try to run through these tests. What's good is, I mean, the Heron team does a lot of different things. I think that they lack some of these types of tests, believe it or not, because I've come back to them and said, hey, Bookie doesn't restart, or, because they're giving you YAMLs to deploy all those things, and or their Heron API didn't restart after a whole node went down, things like that. Sometimes you have to shut down twice in here. I'm not quite sure I ever understood why. I'm going to blame it on Wayne. All right, so now it's powering off that VM. It's killed. So if we go back over here and look at our nodes, we'll find that, again, these don't refresh themselves either, but eventually it will recognize that this thing has gone crazy. Let's give that a minute. Still says it's running. Oh, wait, no, here's this is 5. The names don't match up with the instances 2 and 5. There we go. So now it's showing you that there's a pod this is pending state, TCOP test 2, because that was the one that was running on TCOP test 5. We'll see this thing actually disappear, and it will be deployed on a different instance, because I'm not going to restart 5. I'm going to force it to go to another VM. We could also come over here and see what this guy thinks is going on. So this guy is all red. I thought I could see what instance this is, but it's not letting me. 3, 2. Let me try to match this up here. 2. I think 2 matches this 2. So we should see these like drop off temporarily as well. Yeah. So you'll see that instance has some markers here, but if we go to these guys, they've started to lose. There's nothing happening to the right, and that's because they're dead. This one still has a little nub there. So these are starting to die off. You can see that by the fact that there's no metrics coming back. So if we go back to this guy, stop sliding around on me. Come on. Let's see where we are with Kubernetes. So Kubernetes still is in a holding pattern. Hopefully it's after 1 o'clock, so if you have to go, you have to go. This might take a couple of minutes for it to actually refresh. But in about a minute or so, this will actually recover and start to redeploy. We can look at nodes as well. So this guy is in the question mark state. You drill in, We have all kinds of issues going on now, all unknown. Everything running on it is in a pending state. And it doesn't try to refresh and redeployment right away. It will wait to make sure that it's like not some kind of communication problem first. But after a timeout, it will redeploy all these things.
Now, is it redeploying those to VMs that are already part of your?
Yeah, they have to be an active node, and they have to be a node that has enough resources to deploy it to as well. That's why I kind of picked 5, because there wasn't much going on there. So if you pick the ones that have like a bunch of Kubernetes and Heron stuff going on, then it gets a little problematic with my small set of VMs here. Oh man, let's go back to this guy. I haven't. I have it on my to-do list to, so the idea there is that you should be able to, within Kubernetes, specify that this VM has GPUs, this VM only has CPUs, and that when you define your topology in Heron, the idea would be that you could say, these types of bolts, I want to only latch onto GPU-based VMs or systems, and these bolts can run on a regular CPU, which would actually help a lot in terms of money, in terms of cost, because you could peel out your really high process bolts, force them onto GPU-based systems, and the opposite for stuff that might just be firing off an alert, for example, you could let that run on a CPU-based instance. There's a couple of things there. I mean, Kubernetes is supposed to support that. Heron does not. I've asked that Catholic guy, the guy that runs everything, and he's like, oh, that's a good idea. Everything's a good idea, and it's open source, so they're like, yeah, I want to code it. And it would probably create a new packing algorithm. So that's another thing that they've been working on. So you'd have to create different types of packing algorithms and be specific about and you'd have to talk to Kubernetes as well to know which way to push it. But it's an awesome idea, right? I mean, it would be really very significant for cost savings. All right, let's see if anything's back to life here yet.
You said
Still no.
Kubernetes was blowing out the Mesos
Aurora.
What's the specific benefits that?
Well, Aurora, if you talk to the guys at Twitter, they'd probably not agree with me. But when I was running Aurora, and actually Pete was running it with me as well, we found it to not be very stable.
We found the same thing down at Castle.
Oh, you did that, yeah.
That it was.
So Aurora, I mean, although it was written by Twitter and they use it as their scheduler, we found a lot of issues with it just trying to run it in our local system here. Whereas Kubernetes has been rock solid. I mean, like I've been able to have all these things running, and then we've got someone will bounce the hypervisor and kill all my instances and restart them all, and everything comes back to life. Like I have not had to actually touch anything for it to come back to life. It's been really awesome. In terms of the resiliency of restarts and things like that. It's being slow to get things back on. Yeah, so the VMs themselves have been problematic. Okay, so it did bring up, okay, here we go. TCOP test 2, back to life. It is now on TCOP test 1001 instance. Remember that was on 1005. 1005 is no longer in existence. Okay. So again, it's probably still spinning up a little bit. And let's go back to overview again. Nothing has a question mark or pause on it. Go back to admin. Let me refresh this. Boom. Okay. Perfect. So here we are back at TCOP test 2. And if we start to walk through these, you'll see that they have a gap in their processing, but they're back to life. And the best thing about that is I did nothing, right? All I did was sit back and watch it happen. It's something that, when we're working in our production system upstairs, inside for the customer, we're 24/7 system, and, you hate getting a call at 3 a.m. So if you can let this system prevent you from getting a call at 3 a.m., it's like pays for itself, right? Especially when it's free. But that's to me, one of the best benefits is just the resiliency and being able to restart things as they go along. Let's see how our punching bag bolt's doing as well. Okay, another great example. So here's the punching bag bolt. which was not on the O5 instance at all. It was on this was on container 5. So what did we do? We did 2. We killed container 2. So container 5, I don't know what server it's on, but that punching bag bolt blew up memory. Eventually died out. Bless you. Eventually died out. It sort of says 881% capacity, so that's not good. And what's really cool here is you can see that Heron recovered the punching bag bolt that I crushed its memory on, and now it's running back in a normal state. Another awesome thing. And now that's sort of internal to the container where Heron's managing each specific bolt instance, and then you've got the whole outside of the container control as well, managing and monitoring that. So to me, that's a home run in terms of how this all fits together.
Now, if that VM that you killed comes back online, will it distribute it back up?
It will not. So it will be resources that are available again. So if someone deployed another topology or another, we've talked a lot about Kubernetes managing these topologies, but
or if something else failed, stuff might